start the day very lightly. So when guests travel, we go to meetings, and we see that we are impressed by the sight of beautiful night views. So he decided to send a text to his graduate wife. Now, this was what he wanted to actually send. It says, I had a really wonderful night, and I wish so much you were here. But accidentally, he omitted the E. So right now, if you look at it, it becomes, I had a really wonderful night, and I wish so much you were her. So he lost contact with him after he went back home. I hope that wakes everybody up in the morning. And once again, welcome. So we are living, as you can see, in a very fast-changing world. Now, before the Industrial Revolution, we saw that technology started from Europe. And before the Industrial Revolution, we saw that James Watt actually invented the steam machine. And electricity was also found in the United States. Before the Industrial Revolution, the social structure was more and more of what we call the artisan craftsman, where a lot of things were done at home, and these people were transferring the technology from father to son. Now, because of the innovation of science, it actually advances from energy and also from electricity. This actually changed everything. It changed the social structure. So people, because of the Industrial Revolution, started working in factories. So a lot of people had to be re-educated in order to go back to the workplace. And that not only changed the society, the social structure, it changed politically, and also it affected the economy of the countries. Today, we see that we have information explosion resulting in big data. Now, McKinsey, a management company in the United States, was saying that this will actually change, like the changes, the speed of change will be 10 times faster, and the scope of change will be 300 times larger. Now today, we see that as a result of AI, we're changing even faster. We talk about generative AI, we talk about GPT, we talk about edge, and also cloud computing, and especially semiconductor. Now, many people are afraid that the jobs will be taken over by AI. Now, AI has actually changed, again, the social structure, the political structure, and also, once again, the economy of the world. Now, we are at the moment here to ask ourselves, what should we learn, or what should we teach to our youngsters in college, so that they will thrive in the next not only 10 years, a few decades. This is why I'm so honored to be here opening the ceremony of AMI Academy of Innovative Semiconductor Manufacturing, to witness and to see how we will thrive together into the next few decades. I was actually traveling to Luzon. I was visiting Europe, and I took the liberty of going to Cambridge. And in Cambridge, I was looking at this math bridge that we actually had. This was really inspiring. What you're actually seeing here is the math bridge, which many centuries ago were built by the Great Britain scientists, mathematicians, and engineers. This was built without any nuts and bolts back then. They were relying on the fundamentals of science. Now, a few centuries later, the Great Britain guys were trying to challenge the ancestors, and they took the bridge apart, and they tried to put it back. They couldn't, not without nuts and bolts. Now, even today, with cloud computing, with edge computing, they're still not able to put this back without the nuts and bolts. So that actually, I started by asking myself the question, is math, is the fundamental more important, or is the computer more important? So let's come back and look at, once again, what happened in 1969. You see that Apollo navigation computer was more than half a century ago. As far as I'm concerned, this is the first navigation system in the world for mankind. And electrical engineers started out having 3 C's: communication, control, and computers. And I was also trying to learn from KMITL, or Smart Semiconductor. We all know that from KMITL, we started having telecommunication in engineering, which then started to become the smart electronics. So 3C is what we have. Now then the question was, is math more important or is computer more important? So this very primitive computer is able to actually let Armstrong step foot, to let man step foot on the moon. But if you look at this computer that we see there is about the size of the podiums that we see. And in the middle, you see that these are the displays, and these are the circuits that we actually see. And those are the NOR gates. And to see the size, that is the copper wire. But that primitive computer, which is now sitting in MIT's museum, was capable of sending mankind onto the moon. So they were saying, Armstrong was saying, that's one small step for man and one giant leap for mankind. And I would like to change that a little bit and say that that's one small step for an engineer or one giant leap for engineering. Okay? So the paradigms, as I was saying, we go from Europe, we see what happened in the United States, and it also is coming to Asia. In the beginning, we were also having craftsmen. It's all the same in an Asian country, in Taiwan, in Thailand. We started having family business, and things were being passed from father to son. And then we started having automation. So people started having machines. They work like tools. And also, we started having factories. Also, say for example, the clothing industry, we started having manufacturing automation. Taiwan also started manufacturing, and we have also labor that we have. But recently, as you can see, we started having computers networking and digitizing. I was traveling to Taipei, I was traveling to the United States, and now I'm also traveling to Thailand. I found out that things are really actually very different from what we had 20 years ago. If I'm not able to use the cell phone, I'm not able to travel around. So you see computers, networking, and also digitization has changed the world. And that not only changed things in our everyday life, it has also changed the modality of the work that we have, as you can see. So people are talking about also ChatGPT actually designed chips. So before, you see that people started working at home, and now you see booming, sprouting, a lot of sprouting startups, entrepreneurships are taking all over the world. And this is how the world is changing very vibrantly. Now, so you can also see, let's take a little look at the global AI and semiconductor industry. Now, from the very beginning, you see that from the left there, I'm trying to, okay, the pointer is not working, but from the left there, you see that we started out having IBM's Deep Blue in the 1998. Now, recently, in 2018, we started having the transformers. Now we see that in 2024, we start having ChatGPT. Now we also go to ChatGPT version 4.0. So in order to run that algorithm, we have to have the computational platform, and also the semiconductor, and also the material, the devices that support that. So if we look, we also advance, as I was saying, you see from the computers that actually brought Armstrong onto the moon. We started having, say, for example, the materials, the copper interconnections. Now we go to high-K metal oxide. Now for the lithography, we started going to nano immersion and also EUV. So for transistors, you see that we actually also go into FinFET. In 2012, people are saying that nature has its limits, and Moore's law do not work anymore. Before that, we were trying to get more, less, more. So after that, because of the invention of within that, we're going to have more and more. So we conclude that in order to have large language models on edge devices, we not only, as we witness the semiconductor trend throughout history, we not only have to go for vertical integration, but we're also now going for heterogeneous integration, as you can see for the system of integrated chips, chiplets, and also the 3D. People are also talking about heterogeneous integration in the 3D ICs. Now, we are very proud that Taiwan is the global leader of the world supply of chips. And in 2022, when the numbers were taken, we are very proud and honored to say that we're number one in chip fabrication. We're number one in packaging and testing. And we're also number two in chip design, which is always second to the US on the total production value of semiconductor industry. Now, we have also successfully deployed the 3 nanometers technology, which is one of the most advanced technology on Earth in the world. Okay? And these have been supplied to global companies such as Apple, AMD, NVIDIA, and also Qualcomm. So we are very honored and proud that AISM was launched in October 22, 2021, which is the first in Taiwan. And we're also top one in 2021 in industry income. AISM is also top one in the impact ranking in 2023. We're the highest in terms of the industry income and other funding that we actually have. Out of the world's top 2% scientists, as listed by Stanford University, there are actually 116 designated researchers who are enlisted, and we do have 9 who are associated with our academy, which is the AISM. Currently, we have over 100 students, and annually, so 80% of them are masters, 20% are PhD students. We now have 5 programs and 171 faculty members. So all these faculty members are taken or joined from ECS, College of ECS, College of Science, and College of Engineering. And we do have 5 programs in this AISM that we have here. We have 5 master and PhD programs in critical technologies equipped with more competency. And the core competency of AISM is in artificial intelligence and sustainability. That is why we have IC design, key material, semiconductor manufacturing, smart and sustainable manufacturing, semiconductor packaging, and also testing. Now, I was recruited back to Taiwan. Now, more than 20 years ago, starting about 25 years ago, Taiwan's government was very keen in promoting the semiconductor industry. So they invested a lot of money, and they also went to Silicon Valley to recruit many students. I was an overseas student in the United States, and that was when when we have the CDOT, which is what we call the Silicon Island Project, very similar to the Sandbox program, the semiconductor program that Thailand has. So we have many things in common. So with that, we have national programs. You see that when you have the semiconductor, you not only want to have the resource, you need to have the hardware, you need to have the software. Especially when you design semiconductor, the tech tools are very important. A lot of things are not on the breadboards anymore. We need to have them on the computers. So the national government, actually the Taiwan Semiconductor Research Institute, we have tech tools, Cadence, Synopsys, and Ansys. And these are actually paid by the government, paid from the national programs, and they're free to all the national Taiwan universities, students, and faculty members to do research. In addition, we were also funded to have the Nanotechnology Center and also the Precious Instrument Center and the Instrument Center. So these are all the stuff for the smart manufacturing technologies that we actually see. So NCKU is also proud, and we're very honored that a lot of our alumni has actually made a difference, especially not only in academia, but also in the industry. Among the 5 categories that we have, you see that we have TSMC for the semiconductor manufacturing, UMC, we have Winbond, Micronics, and also #1 packaging company in Taiwan, ASE, and I'm sure you're all very familiar with Delta, who's collaborating also with AMITL as far as I understand it. So we saw that. I also know that many of us, the VPs and many of the professors of this university actually got their degrees from the United States. Now, if we remember, for the East Coast, I-95 was actually traversing through all top Ivy League schools in the United States. Harvard, Princeton, and you see Columbia, all the way down to the south. We also have Brown. So we are very proud that the National Highway of Taiwan, Highway #1, is a very similar method. We call it the Taiwan Semiconductor Belt. So when you go from the north of Highway 1 to southern Taiwan, you witness all the necessary semiconductor in all these 5 areas. So we are very honored to say that we in Taiwan are able to produce and do semiconductor starting from scratch, 0. Okay, you see that all these companies, and also we're honored Mr. Bruce Chen, the founder of Delta, and also Ming Wu, CEO of Micronics, and Dr. Ming Shen Wu, the chairman of Himax, who's IC Design, and also Yajou, who's also working with many universities in Thailand. They're top leading industry leaders who have influenced the semiconductor industry. Now, recently, I have set up an industry forum to connect friends all over the world for industry forum, for academia and industry. Now, we witness that in order to put large language models at your fingertips, I invented the head of AI from MediaTek. And in order to do that, we have to not only do vertical integration, which starts from algorithm to architecture, and then it also goes into process. So we see the keynote from PY, and I'm also very proud that our students from NCKU, especially the one who got his PhD, Mr. He Yuan Ling, is also contributing a lot to the vertical integration. Now, another student of mine, also NCKU, was the co-inventor, Mr. Ethan Tsai. He's the co-inventor of the 3 nanometers technology. So when we had this back in March this year, Ethan was telling me that, sir, we have made a difference in the semiconductor, not only in Taiwan, but all over the world. So you can actually see that. He was telling me that Fab 18 is TSMC's largest fab. So this is actually the largest fab on Earth. And they were actually producing, we already have mass production for the 3 nanometers technology. And you see that MediaTek, Apple, and Qualcomm are actually also coming out. So Ethan is also from NCKU, and he's also related to our AISFM. And more than 50 years ago, you see that when mankind set foot on the moon, the circuits were copper wires, you see the NOR gates. But now, when we visit this again, TSMC actually have 3 nanometer chips for smartphones, and also high performance computing. So this is how we see what we have achieved today. That is the difference that we have made. Now, as we see in electrical engineering, we used to talk about, as we were saying in the beginning, computers, communication, control, and circuits. We also see that, like Germany, the car is also very car electronics. Now, ladies and gentlemen, we have forgotten that we have omitted the E in the very beginning. Let's put the E back. So in addition to car, we also have care, healthcare. So rather than having 3 C's, we have 6 C's. Now, from Taiwan, from AISSM, we would like to reach out to the Silicon Global South. So NCKU, AISSM would like to collaborate and with KMITL, SEM, and we're very honored to be here to witness the history of opening of this KISEM of KMITL. And we have already made a difference, and we would like to invite KMITL to change the world together. Thank you.
Such an incredible presentation. And next, such an honor today that we have another chairman from Shanghai University. May I ask for a warm round of applause for Professor Ruiba Zhang in the topic of semiconductor education challenges and experiences sharing.
Thank you. I'm very honored to be here, and I'm from Shanghai University, and I would like to talk about conductor education, and I would like to mention some challenges and share some experience. Okay, right now, more people realize the importance of semiconductors. This is because of the intelligent devices everywhere. So that's why chip shortage affect automotive industry. Then we would expect more chips to be needed for AI. So AI needs a lot of high performance calculations. So must consume more chips. And we know that we have a fragile supply chain for semiconductors because only the supply chain is controlled by very few companies. And the trade war between China and the United States also will have a strong impact on the semiconductor companies and also provide more opportunities. So before we talk about education, I would like to discuss what you need for semiconductor technology. Okay, of course that we know the Moore's law, but the chart here already show that Moore's law already changed. So in the future, we were looking for new method and to breakthrough because of the power consumption. Okay, so that will be important in the future. Because of the Moore's law, that means we need to update the technology and also the textbooks. And the other feature is the integration, which related to different fields. And I would like to show an example of strand silicon technology. This technology is used to improve the transistor behavior. However, people want to improve the performance, and they need to produce some negative defects. And the defect will produce mechanical stress. This will change the distance between atoms and to change the energy band. Then the carrier mobility can be improved and the circuit speed can be one of the features. And another feature is that the monolithic integration, that we use hundreds of steps to make billions of transistors. Right now, it's not only hundreds of steps. We have more than 1,000 steps. We can make trillions of transistors on the wafer. So what's the problem with the monolithic integration? That is, one mistake may kill all. So that is very important to control defects. And the plot should show you the yield curve. So that means the production yield is very sensitive. That's why it's very difficult to duplicate the experience. And this is also one of the features for the semiconductor technology. Okay, then we talk about some challenges in education. So first is the talent shortage, because not everyone has the opportunity to access semiconductors. And very few people in semiconductor industry would like to go to schools or teach because of the gap between the academic units and the companies. And of course, to build up an environment for semiconductor education is very high cost. Not only for parents, but for chip out, you need to have the companies. They would like to provide shelters. Okay, so the students can design their circuit and to make that in real chips. And we also need to have some supporting system. So that is why AI is here. Okay. That is very important. And we also need to update our knowledge or our teaching materials to keep up with the industry. And later I will show some examples. And of course, we need to combine different fields in studies. So this is one question: how to explain VLSI to students? From the top, we can see an integrated circuit, but we also need to look at the chip from the conceptual view about the semiconductor device and the process. And the student need to combine all the concepts together. And we need to build the environment, allow the student to have the concept. So it's not easy. And I'm talking about a supporting system. Even though we make the environment, we need to verify if the environment is okay for the semiconductor technology. Then we need to do some measurement. And for the feature of the semiconductor technology, the measurement, okay, we have a large range of the detecting limits. And for the material analysis, and we need to analyze the concentration of the doping level, dBm, with the depth resolution to about 10. So we need some other supporting systems so we can analyze or to do some verification. But usually, sometimes we need to go And when we set up everything, we need to think about the progress of the technology. So the plot just show you that the distribution of the retention time in DRAM, the retention time determine failure rate of DRAM. But at the left side is the previous research. They just test for 1 million DRAM cells. But after about 10 years, people already make 1 million cells. So the behavior changed. But how about the textbook? Right? We need to think about what's going wrong. Okay? So in the past, 10 years ago, we believe the value mechanism, okay, maybe is just like the paper published in 10 years ago. But right now, we have new technology. Can we teach the same material to our students? That is the question. Okay, so let me share some experience about Taiwan. And actually, Taiwan started to develop semiconductor technology around 1970. So the government just established an organization called FIRST. The organization was supported by government, but all the members are not government employees. Okay? And their mission is to develop the semiconductor technology. But the goal is to gear toward industry. So for the first generation project, also spin-off UMC. Then for the second generation of the project, also spin-off TSMC. And in 1990s, also started the micro project, and I was there. But after the project, TSMC acquired the whole project team. Okay, and you probably know the MediaTek is the top 1 fabless company in Taiwan and around top 5 in the world. Actually, MediaTek is a spin-off from UMC, and the leader also was a member in so before. And our university, CGU, we built our semiconductor lab at the late 1990s. Together with Nanya Technology, is a different company supported by our Formosa group. So when our group decided to develop semiconductor industry, then they also set up a semiconductor lab in our university. So when we build up our semiconductor facilities, we need to think about what the company needs and how to keep the efficiency. Okay, because we know that to maintain the period will need a lot of financial support. But we cannot afford the cost like a fab. So we need to think about how to cooperate with companies and how to co-work with the national lab that was supported by our government. We have the support from our hospital system. So we also need to plan how to do some cooperation in the future. So that we can keep children. Also, we need to pay for maintenance, but we can amplify the research result. So this is our plan. And recently, we just have another joint program with memory companies. Just like the guests from NCKU mentioned about their new college for semiconductor. That is supported by government. But our program just no government supported, all by companies. So this is our strategy. So we will have a program just 1 year in college, the other year for internship in companies. And the company totally support our students. And after graduation, they can stay in the company. So this is a win-win strategy. So this is our experience. Okay, so thank you for your attention.
So now let's watch a video presentation on the activities of Kaizen. Next is collaboration to